It's an honor and privilege for me to introduce the first plenary speaker of this conference, Professor Michael Jordan. He is a P. Hong Chen Distinguished Professor at UC Berkeley, with a split appointment between the Department of Electrical Engineering and Computer Science and the Department of Statistics. Professor Jordan's research interests bridge the computational, statistical, cognitive, biological, and social sciences. Professor Jordan is particularly known for explaining the links between machine learning and statistics. He has popularized important statistical methods, such as Bayesian networks, to the machine learning community, and formalized machine learning methodology using statistics. In 2016, an article in Science named Professor Jordan as the most influential computer scientist in the world. Professor Jordan is a member of the National Academy of Sciences. He is a member of the National Academy of Engineering, a member of the American Academy of Arts and Sciences, and also a foreign member of the Royal Society. Please join me in welcoming Professor Jordan to the stage for his lecture on uncertainty, asymmetry of information, and statistical contract theory. Welcome.
Thank you very much. It's a delight to be up here again. My first trip to Europe was to Stockholm, and it was sometime in the 1960s when half of you were not yet alive. So a couple of comments about what you already see on the page there. First of all, I have been in Berkeley for 25 years, but this year I've moved to INRIA in Paris. I'll start a career in informatica, informatique. Second point is that it was a surprise to me in 2016 to be named influential computer scientist, because I'm not a computer scientist. I don't know much computer science. My actual formal training was in control theory. So I took an interdisciplinary program at University of California, San Diego, back in the 80s when I did my degree, and there were no classes, so I just took control theory classes, in particular optimal control theory. And I must say that that kind of mother discipline of putting modeling together with optimization and dynamics stays with me to this day and informs much of what I do. What I'm not is an AI researcher, and I resent that terminology being applied to us engineers. And I'm going to spend a few of my moments at the beginning saying a little bit of why. It's become so predominant that we have to say something about it. A little bit about not so much where it came from, but what people really seem to mean by it. It's a very unfortunate terminology in my view. So let me start with that. Academics tend to focus on academic ideas. And so they talk about the history of intelligent systems through the lens of cybernetics, artificial intelligence, and then something you may have heard less about, but something called intelligence augmentation. So we have our friend Norbert Wiener there. Cybernetics was his grand vision that really, in some sense, systematized control theory, but he had a broader vision. He was a mathematician and wanted to put it in a broader context. Around that same time, John McCarthy coined artificial intelligence, and really they were both at MIT at that point. They had moved there, and they disliked each other. In particular, McCarthy wanted to separate himself from Wiener, and so he invented this term for that reason. He was a logician and computer scientist. Really didn't have a lot of continuous mathematics in his approach, and not much uncertainty, and very distinct. Weirdly, what's happened over the last 50 years is that Wiener's perspective has dominated. We have these large-scale systems that are networked and federated, and they work with uncertainty and continuous variables. It's now often called machine learning. And now that label is being called not cybernetics, but being called AI. So it's a strange fact of history. Now, the other thing that happened, however, after about 1960, we never really have gotten AI. AI, in McCarthy's vision, was that the computer would do the thinking. It would be intelligent in our way. We don't have that. We have large-scale, massive data analysis that does surprising things. But what else has happened other than things like just Internet of Things and connections is something which is called IA. And there's Douglas Engelbart, who also kind of fought with these people, in particular with McCarthy. He thought the computer shouldn't replace human beings or be as smart as humans. It should augment human intelligence. And that's arguably what's happened, really. The search engine is not itself intelligent in indexes web pages, but it's augmented all of our intelligences in unforeseen ways. And that continues to this day. Systems that do automatic translation and so on augment our ability to communicate. And I think that Engelbart was really onto something. Now, I really don't think that's the right way to think, though, is to put on your academic hat and view the world as flowing from academia. A lot of great ideas are developed in academia. But really, in the real world, something else has happened. It's often called machine learning. I don't think machine learning is a separate discipline. I'm going to kind of argue it's a blend. It's kind of an engineering field. It takes tools and solves problems. And it really arose already by, say, 2000. It was at the back end of companies. So you didn't hear much about it, but say at Amazon or Alibaba, you had the world's largest supply chains. In fact, so Amazon takes about 1 billion products, puts them together, multiple pieces all around the world, and ships those to hundreds of millions of people within a day, or 2 or 3. It's the world's largest stochastic control system by, I think, any way to think about this. And it couldn't have been designed by a human using a textbook. All right, so how was it designed? It took vast amounts of data in, all the logistics data coming in from around the world, ships and boats and strikes and factories and so on. It ran an algorithm on it that was a gradient descent algorithm. It was random forests. That was kind of the neural network technology of the day. It's about as good as neural networks, just a little different, has some disadvantages. And you couldn't do that on one computer. So they started to run it on not just tens of computers, but thousands and even tens of thousands of computers around 2000. That was the beginning of the cloud. The cloud arose at Amazon to run machine learning workloads using random forest on supply chain data. Okay? And it worked. In fact, I visited there around 2000, and it was quite amazing how good the supply chain was. And the engineers working on it said, it does surprising things. It comes up with solutions to supply chain problems we never thought of. Okay? So a glimmer of what we're talking about today, but no one had articles in the New York Times about it. Next phase for me was when they realized they also had data about human transactions. It wasn't just about supply chains, it was about human buying behavior. And they could use the same machinery, the web, the cloud, the algorithms, random forest, and then the data is now human data, transactional data. And that led to things like recommendation systems and new kinds of commerce. The first 2 bullets really are billions of dollars of productivity gain. It had a huge impact on the world and continues on to this day. Not really talked about so much, but then what happened? In the 3rd generation, people also realized they had data from human beings. Speech data, vision data, data that reflects human activity. You had the whole web. And so they ingested that in, they put that in the same pipeline, basically. Now we don't have random forest anymore, it's neural nets, but very similar. We have the cloud, we add GPUs to it, make it go a little faster, and we have massive amounts of data. That latter is critical, of course. And then it starts to do surprising things. It looks kind of human-like. It can do things that look like us. And now this AI phrase that had been dead and dormant for 40 years came back. Okay, so in my view, that's the history. But what I always like to look forward is to look forward, and I look forward and I see something different. I don't see AI emerging and a super intelligent entity. I see bigger and bigger networks that connect people in new and different ways, and maybe new democratic mechanisms and new ways of designing economics mechanisms and so on. So some say it's cybernetics writ large is the vision I see coming forward. And I want to dive into that in this talk, sort of what that vision is, but really then I want to about at least halfway get through talk, get to real problems. And I'll give you theorems and necessary and sufficient conditions and so on and so forth. So it's a math talk, but it'll take me a moment to get there. Okay, so just again, what McCarthy was saying in the 50s, you're going to take an individual human and you're going to figure out what's happening in their head and you're going to put that in a computer and then you'll amplify that. Now that's a fine philosophical aspiration. It excites young people, and so on. But as an engineer, it's not really clear what the engineering goal is. You take a working system, you take out a human, you put it in a computer, what changed? What's better, what's worse? Not clear. It's not the right level to design an engineering system. You design at the level of the system, which may include many, many people and many, many computers connected in new ways. That's the level to think about. And I don't have to say that in this audience probably too much, but you never see it talked about this way in the newspapers. It's always about the superintelligence and the Elon Musks and all this kind of nonsense. All right, so another way to think about intelligence, first of all, is to realize intelligence isn't just human intelligence. We're intelligent in some ways and not intelligent in other ways. Ant colonies are intelligent in certain ways. Economies are intelligent in certain ways. There's all kinds of intelligences, right? And so we can start to see that our overall systems, our planetary scale systems for doing finance and transportation and healthcare, have their own intelligence, just like any economic system has something of a robustness. It can change, adapt, it learns. And so this economics perspective has not really been part of the dialogue, and I'm going to emphasize that here. So it's not just about connections, it's also about economics and design systems that have incentives in them. Okay, now the last little bullet on there is a key technical issue. As I alluded to, McCarthy had a vision of logic as the formation or the foundation of intelligence. It didn't really work out. Logic is not a very good language for these kind of systems. And in particular, it doesn't handle uncertainty very well. And if you look at these wonderful large language models, ChatGPT and all, they're good at many things and they'll get better over time. What they're particularly bad at is uncertainty quantification. If you ask them some question and you say, and it gives you an answer back, and you say, how sure are you of that? It doesn't know what to say, basically. It doesn't have a model of uncertainty. What it will do is take some phrase in the past where some human said, in response to how sure are you about that, they said, well, I'm sure, or I'm not sure. And they will kind of copy that. Okay? That's really terrible. You cannot interact in our world with all the uncertainty without having a model of uncertainty. And moreover, humans individually are pretty good with uncertainty, but really we're good in groups. That's what groups really, really do well. That we mitigate uncertainty, we model it, we watch each other, we learn from each other, we mitigate uncertainty. If we put these new entities in our midst that don't do much with uncertainty, that's a problem. Okay, so I want to have uncertainty incentives and then information asymmetry. That's an economics term. We're going to have these collaborative systems, and collaborative systems are going to be strategic. There's different parts of it that want to have different goals, and they don't want to give away their secrets, and you'll still have to interact with them. So economists talk about this all the time, kind of contract theory and mechanisms that take into account information asymmetry. All right, if I'm working with you and you know something more than me, you're not going to just give me your knowledge. I'm going to try to incentivize you, and you'll do something, and hopefully good will happen out of that. So we all know about this way of thinking, but it's not that common in engineering to talk about this. We talk about Nash equilibria, which are symmetric design. Stackelberg are these asymmetric kind of designs, and we don't see as much of that. Even in this conference, I looked through the kind of game theoretic sections. A lot of Nash came up, but not much Stackelberg, somewhat surprisingly. All right, so we've got to think about these information asymmetries. Information asymmetry is a kind of uncertainty. If I'm interacting with you and I don't know what you know, I'm uncertain, all right? But I'm not going to take that away by simply sampling and getting more data and having the law of large numbers kick in. Okay, it's more fundamental than that. All right, now if you ask a machine learning person, don't you work on collective mechanisms? They'll say, sure we do. It's called federated learning. All right, so what is federated learning? Well, it's basically a decentralized kind of learning system. It has a server which wants to take in large amounts of data to build a large-scale model, maybe a language model or a speech model. But the data lives at the edge, and the data is like on cell phones. And so the central model wants to flow all that data back and then build a model and then send the model back to people in some sense. Now you need to compress things, and you have to guarantee privacy and all that. So immediately there's some technical problems to be worked on, and people have. But this is a very limited vision of how people interact with some kind of a central service. Just giving things and then getting something in return, hopefully. It's not really how people want to interact with the world. More and more people create things on their cell phones. They write a song, they write a novel, they interact with each other. All kinds of things are happening on cell phones. Having companies simply take that data and then use it to build a model that they somehow then monetize is a very, very broken way of thinking about economic value, of creation of value and management of value, participatory mechanisms. It just doesn't have any of that flavor. All right. So just to make this very concrete, I've been involved in something I'm quite proud of for the last 5 years in a company called United Masters. I've been a scientific advisor. I'm now on the board. The CEO is Stephen Stout, who's a legendary hip-hop producer in the United States. And this company is a three-way market. We created it with that multi-way market idea in mind. Young musicians are making songs now more than ever before in history. People between 15 and 20 typically make most of the songs, and they listen to most of the songs. It's not that everyone's listening to a few famous people. It's young people doing this. But they're not making any money off of it at all. Okay? And it's really broken, and they can't have a job. Once they become 20, they have to do something else. So what we've done here is to create a market where there's now 3 million musicians have signed up in the United States. They come onto the market, their songs get made and mastered and produced and distributed. There are people then listening to them, they're connected to their listeners, so there's a little bit of a market already there. If I'm popular if I know someone likes my songs, I can propose to come play at their wedding or something. But more importantly, there are also brands. Brands include the National Basketball Association, that includes FIFA. And so they have contracts now with the United Masters. So if you hear a song on the FIFA website or on the NBA website, that song is being streamed from United Masters and the musician gets paid in that moment. Moreover, the other brands look at that. It's part of a market. And they say, oh, I see that musician is popular on the NBA website. That's a demographic that appeals to me. I'm going to reach out to that musician and ask them to write some more songs and work with me. And that's happening to this day. So this is a way that market creation, AI as in creation of a market, not simply writing an AI program that creates music. That would be a bad idea. Interesting, but a bad idea. Instead, empowering people to connect to each other in new ways that allows them to value their product. And so now we have 3 million people who are actually starting to make something like a salary. That they didn't have a job before, they have a job with this kind of way of thinking. Okay. I think this can be done in all kinds of systems. Last point before I turn to more of my technical part of the talk is recommendation systems I alluded to are very important in machine learning. They're a pattern recognition system. They make predictions. The better the predictions, the better the commerce. So you all know about them. There's some kind of a matrix factorization. But machine learning people don't think about the economic model really at all. So they don't think about what if there's competition. So if I build a recommendation system and it recommends books to people, and it works now at scale, all of Sweden is using my system, I could recommend the same book to 10,000 people on some day, easily. If all of them want to buy it, then I have to copy the book. But I can do that. There's no scarcity in the world of books. Movies, obviously, same thing. I can copy the movie. But if I start recommending things where there's real-world entities, like restaurants, I could recommend the same restaurant to 10,000 people. And all of them will go, and I'll create congestion. All right, so the networking people certainly know about this kind of phenomenon, but machine learning people don't think about it at all. They just create systems that create problems like this, congestion. And then they worry about having to fix it by somehow doing some load balancing. That's not a good way to think about economic value. You can't simply give the entity to the first person to arrive. That's not if you did that for like college admissions, the first person to put in their application would be admitted and no one else. That would be a terrible mechanism. Same thing with recommending streets to drivers. You can recommend the fastest route to the airport to everybody, and then it becomes no longer the fastest route. All right. So again, economics people know about this a lot. All right. But what's missing is the economic thinking doesn't have a lot of data analysis. It simply has a mechanism, an auction or something, but there's not a lot of collection of data and then adjusting the mechanism. It's not adaptive control, really. Okay. So I've alluded to these academic foundations. Let's return to that for just a moment. Everybody's a computer scientist, and that's where the algorithms come from. But computer scientists don't solve a lot of problems all by themselves. They develop a device on which you can solve the problems. They're sort of natural collaborators in some sense. Who do they collaborate with? Well, eventually they started collaborating with statisticians. The computers gather data and then analyze the data. And that's what machine learning is. It's just simply a bipartite relationship between statistics and computer science, inferential algorithms. What about statistics meets economics, where we start to have incentives? Well, first of all, statistics, computer science, machine learning, as I've alluded to, has very little economics in it. Very little incentives, very little mechanism design, so on and so forth. Some, but very, very surprisingly little. So it's missing economics. Did statistics ever interact with economics? Well, yeah, that's econometrics. But econometrics is also very limited. It's basically about measuring the economy, okay, doing time series analysis. Okay, not a lot of algorithms and mechanism design in econometrics. What about economics meets computer science? There must be mechanism design there, and yes, there is. That's called algorithmic game theory. It's mostly about the design of new kinds of auctions, mostly. There's almost no statistics there, so no data gathering and adjusting the mechanism over time. All right. Now, when I say statistics, economics, and computer science, I don't mean those fields literally. I mean that way of thinking, inferential thinking, incentive-based thinking, and algorithmic thinking. You might ask, where's control theory on this? Well, in some sense, it's everywhere. Control does all of these things. All right. So, but why? So, when I put this diagram up there, I have in mind sitting at places like Amazon, where I work a day a week, and seen a new problem being proposed. Like, we've got third-party sellers and they're doing this and that. We've got to motivate them, incentivize them. There's this value. And it's a hard problem, so you need like 10 people to solve it. And you have people around, you have a computer scientist, you have a statistician, you have an economist, probably an operations research person. You rarely have a control theorist. So why is that? And so that's kind of what I want you to ponder a little bit. And I think one reason is the control theorists don't tend to work with huge amounts of data. And so they didn't take advantage of the huge wave of infrastructure that created large data flows. And they viewed it as ad hoc to take data into account. It's not ad hoc. There's theorems you can prove and it works, and so on and so forth. You could do it worst case, you can do it without assumptions and so on, non-parametrically. So that's kind of one problem. And then it's kind of the class of problems I think that a lot of control theorists work on. It's one where a small team of control theorists can solve the problem. And you don't need a lot of collaboration with economists and computer scientists and statisticians. So that's one perspective on why control theory is not there. In some sense, it's everywhere. In some sense, it's nowhere. But I want you to think about that. OK, so finally, to the rest of my talk. So I'm going to sort of give you some little vignettes, little problems I've been working on for about 10 years now that blend these three fields in I think some new ways. These are not just old problems kind of brought up to the modern era. They're new problems. The new mathematics is needed. And I'm going to pick like 2 or 3 of the vignettes. And I'm not going to probably go a lot into here the derivation. The papers are full of all the math. But I will show you probably a theorem here and there. But really, it's more the setup of the problem. How do we set up the problem? What is the problem? And then you can imagine how you would solve it. And at the end of it, you're going to see some things that are not that unfamiliar. Now, I in some ways would most like to start with that first bullet. That's where I spend most of my time, but I'm not going to do it at all. I'm just going to have one slide on it. So in machine learning, we're very good at talking about optimization nowadays. It's not just old-fashioned optimization. It's not just convex optimization. It's very large scale, billions and billions of dimensions, tens of billions of parameters, and it's non-convex, very much non-convex. But we have theory for all of that, okay? Surprisingly good theory. Now, moreover, we are able to do this in the stochastic domain. We're able to do this upper and lower bounds of rates that are actually good rates, and they actually characterize real behavior. We're almost done with some of those problems, right? But the problems I'm interested in the last 10 years are not just about optimization. They're about finding equilibria in economic systems, and those are not optima. Okay? So how do you have algorithms now in 10,000 or a billion dimensions that find equilibria? Okay? That's not been that much work on economics on that. Fixed point theory is kind of the underlying mathematics. But how do you do fixed point theory in very high dimensions with non-convexities and stochastics? Lots of open problems there. And then lastly, it's rarely about just equilibria. Everything is always moving. So it's about things that track equilibria well in high dimensional spaces. So the dynamics is critical. Okay? So for the young people in the room, these problems are wide open. There's all kinds of interesting things. A lot of the mathematics is variational inequalities, so things you're probably familiar with. Variational techniques are very, very important in this. And so let me just say on one slide some of the things, some papers of my group in the last sort of 5 years, where most of these papers have actually solved a problem. They didn't completely solve it, but they got pretty far. So I'm just going to briefly do some advertising here. They're all on my homepage if you're curious to see them. The first one took a Lagrangian and Hamiltonian perspective on optimization. This was actually pretty critical. It took everything into continuous time and then did Lagrangian Hamiltonian symplectic integration to go back to discrete time. And those steps allowed us to get characterization, if and only if, statements about when certain phenomena would arise. You couldn't see it in discrete time, where like the Nemirovsky and Nesterovs have worked all those years. You couldn't see certain phenomena there. If you went into continuous time, you could see the phenomenon. Okay, so that paper started to set that up a little bit, and then everything else after that was in continuous time. The next paper was about non-convex optimization. So what if you're approaching a saddle point in high dimensions? It could take you exponential time to get out of the saddle point as you find that one eigenvector that pulls you out, or it could be polynomial time or whatever. It turns out to be polylogarithmic time. Surprise, this was a shock. That paper is probably the most surprising. And the analysis there used high-dimensional probability theory to actually do, instead of doing differential geometry, it did probability theory. It took some coupling between stochastic processes. The third paper is with my colleague Mike Muhlenbach, who's a control theorist working in Switzerland originally. And here we're back in continuous time, but we're putting constraints into the problem. So in continuous time, you can put constraints not simply kinematically as boundaries and projecting onto them. You can put them as forces. And so we have a continuous time framework for non-convex optimization. Convergence to saddle point I already alluded to, so we've worked a lot on variational inequalities. There's a lot of work there on converging to saddle points only in an average sense. That if you look back over time, you see the average behaved well. That's not good enough for actors acting in the moment. They don't have that average. They don't have the joint average. So they have to have last iterate conversions. That's really key. So we've worked a lot on that with Tatiana Chavdarovda. We have some work that uses high resolution differential equations. These problems, if you take the discrete time, you take it into continuous time just naively, you get some differential equation. Often that differential equation does not give you the phenomenon. So there's different limits you can take to get these things. All right, again, there's more work on variational inequalities. And then the last paper I'm particularly proud of, recent paper, where that word adaptive is actually important. Almost all of this work have step size parameters, some high hyperparameter. And it's sort of mysterious often how to set that. That's where it becomes a little ad hoc. In that last paper, we started to look at algorithms which are adaptive, which they will work even though you don't know the step size parameter in advance. And they're not simply doing line search. Okay, so that was 5 minutes on an area that I care much about, but I'm not going to talk about. Okay, so I'm going to give you some little vignettes now that finally bring together economics with statistics with computation to solve real problems. And so let's start with one on contract theory. All right, so contract theory is a part of economics that I think is really interesting. It's about asymmetries of information. It's about Stackelberg equilibria instead of Nash equilibria. But it hasn't been statistical. And so with my colleagues, we've turned it into something statistical. All right, so one slide on what is the theory of incentives. There's a book on the theory of incentives, Lafont in 1970, Lafont and Martimore. As I'm sure you all know, the mathematics of economics, there's many kinds of mathematics, fixed point theory, various dynamical systems, but in particular is game theory. All right, but game theory is like forward dynamics. Okay, it's like, physics. You write down F equals ma, and then you integrate that up, and you see the consequences of that model. And if it looks like the real world, you say, hey, I got a good model. Right? But an engineer wants to go backwards. An engineer says, I want some behavior in the world. What differential equation do I design to get that behavior? So that's like mechanical engineering. In economics, game theory says, if I set up a game in a certain way, here's the agents and here's the payoffs, and then I run that, I'll get some behavior. There'll be some allocations and some prices and all that. Does that look like the real world? If so, then I had a good model. And that's what a lot of game theory classically is about. That's what von Neumann was doing. An engineer wants to go the backwards direction. They want to say, I want some behavior in the real world, that allocations happen a certain way, there's some efficiency. What game do I design to achieve that? All right, now, there's different kinds of game theory. You could have simultaneous games where agents come in, they don't know each other, they play something, and then you ask for a Nash equilibrium. The inverse of a Nash equilibrium, that's an auction. So that theory is pretty well developed. But the more interesting equilibria are often sequential ones. And they have dynamics, so they're Stackelberg equilibria. So some agent who's the leader does something, the follower gets to see that, and they condition on that, and they act. But the leader knew the follower was going to see what they were doing, so they thought ahead. So it's game theoretic still. And Stackelberg equilibria are probably more characteristic of more real-world phenomena than Nash. And now you can ask, what happens when you go backwards in Stackelberg? Well, that's what contract theory is. So contract theory, you actually all know about it. It most famously arose in the 1980s with the airlines. The airlines before 1980, I remember well, there was one price for every seat on the airplane. And you might imagine it's not too efficient economically because some people are willing to pay a lot and some people are not willing to pay so much, and it gets amplified. And so in fact, they would try to set a fairly high price, and you'd only get a few people on the airplane, or they'd bring the price down, and the airline would be full, but they'd lose money. And so these low-cost airlines came, and they started just simply bringing the price way, way down, and they got the airlines to be full, and they took people away from the other big, national airlines, Alitalia, Air France, and all this, and they started to win, and the national airlines started to die. Pan Am died, Braniff died, so on and so forth. They all started dying. Air France didn't die because, of course, the French wouldn't let that happen. They put a lot of money into it. All right, now the low-cost airlines didn't really have a great economic model. All they wanted to do was to kill the big airlines, and then they would take over. All right, so somebody, an economist at American Airlines said, wait a minute, you need to do contract theory. Contract theory is that you have different classes of services and different prices. All right, now ideally I would look at someone and I'd say, oh, that person, they're wearing a suit and tie, they look like a wealthy, professor. I'm going to charge you 1,000 euros to go to Helsinki. Whereas some student comes in, I look at them, I say, they're not going to pay 1,000 euros. I'll charge you $100. So I do this triage as people come in. That's called first-degree price discrimination. It doesn't work very well. Why? Because he watches that. The next time he arrives, he's dressed like a student. Of course, he had to spend money to buy the clothes, so there is this. All right. So how can you fix this? Well, you do what's called third-degree price discrimination. What you do is you have a menu of options, and everybody gets the same menu. You have a service and a price, and everyone gets the same. And then they self-select. All right, so for the young people in the room, you're not going to know about this thing, but there's this thing called business class. And in business class, you go in and you pay a lot more money, and you get a little glass of wine, and you get to sit in a slightly bigger seat, and you're in the front. And a lot of people are very proud to be in business class. They feel very good about themselves. All right, the students walk past them, and they feel very good about themselves, too, because they paid 100 euros to get on the same airplane as these dumb people in front. And the airline's very happy, too, because the seats are all full, and some of the seats, they charged a lot of money. It's win, win, win. All right, so they did this in the 80s. American Airlines bounced back. They made enough money. They killed off the low-cost airlines, and all the airlines started to do this. Now, you may not like, then they have, stay overnight on a Friday. You get, blah, 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 all kinds of rules. These are all price discrimination, but they're third degree. You might not like this, but you wouldn't have the airlines without this. Efficiency is sometimes needed. All right? Now, what's problematic about it is they don't use much data to do any of this. They just have some smart economist sitting in some room crossing curves and finding points where things intersect. And they adjust it really on the fly and so on. That's no good. So we want adaptive mechanisms that are transparent, that we understand the statistical properties of them, that are running our systems. Okay, and we don't have that. Okay, so now let's get back to a real-world problem that I've actually worked on. So clinical trials. In every country, clinical trials are run every year to decide what drugs go to market. You do tests on all kinds of things, and no one knows whether it's going to work. You try it out, maybe it works, maybe it doesn't. So we all remember with the vaccines, this was done very effectively. It costs tens of millions of dollars to do clinical trials for every therapeutic area. Very importantly expensive part of our lives. Why is it so expensive? Well, these are A/B tests. You have to say, I think it was 36,000 people were used for clinical trials for the vaccines. That costs a lot of money. All right, so is it being done well? Is it efficient? Well, it's using sort of nice economics ideas in some sense, but it's using mostly statistics ideas, and the two together aren't being put together in the right way. All right, so I believe this should be thought of as a contract theory problem. You have a principal and you have an agent. The principal is the regulatory agency. Okay, we talk a lot about regulation these days, but we don't talk about contract theory. Okay, so I'm going to try to put these two together. So the principal is like the FDA in the United States. So they only have partial knowledge. Here's some drug candidate that comes in, some protein that someone designed in some lab somewhere, or peptide or whatever. They look at it, they may know a little bit, they don't know much about it. So they have to test it. So they run a clinical trial. Okay. Now, on the other hand, where do these proteins come from? Well, they come from the pharmaceutical companies. Pharmaceutical companies are generating the candidate hypotheses, and they're self-interested. So these aren't just random hypotheses that some scientist is looking at. Okay. Now, does the pharmaceutical company know more about the protein? Of course. They worked on it for many years. They put their engineers on it. They tested it a little bit internally. They still don't know whether it really works or their side effects. So it's exactly an information asymmetry problem. The FDA cannot say to the agent, tell me the truth. Tell me everything you know about your protein, okay, for competitive reasons and strategic reasons. All right, so does this work? Well, you can now put on your statistics hat, and you can say, well, as a statistician, I know how to do A/B testing, and it's a yes/no problem. And so what I do is I have two kinds of drugs, bad drugs and good drugs. Theta is equal to 0, theta is equal to 1. The bad drugs don't hurt anybody. We screen for that, but they don't do anything. They're just ineffective. And a lot of drugs on the market are like this. They don't really do anything. The good drugs actually have a nice effect. And so the FDA designs a clinical trial, so the probability of approval of a bad drug is controlled at, say, 0.05. It's actually about 0.01, but anyway, roughly that. And the probability of approval of a good drug is, that's the power, is around 0.8. And they work very hard to get these numbers to be really good, non-parametrically, robustly, and so on. They're really good statisticians. So you could ask, is this a good protocol? This is what the FDA is doing. Should they be, is this good? Well, it's optimal protocol. It's optimal. It's the Neyman Pearson test. And if you did a statistics class, this is the optimal protocol for a type 1, type 2 error control. hypothesis. But it's not a good protocol, I'm going to argue. Why? Well, let's think about case one where you might make a small profit. So it costs you $20 million to run the trial. As we saw, that's kind of typical. And if you're approved, maybe you might make $200 million in 1 year. That would be a small little niche drug. And now the CEO can look at all the numbers on the page up there and she can do the calculation. If counterfactually, my drug is not good, theta is equal to 0. Now, I don't know that, but let's imagine for a moment a world where that's true. In that world, I throw the candidate up, it's not an effective drug, and my expected profit will be minus 10 million because I have to pay this entry fee. So I look at that and I say, well, I'm not going to send, I tell all my bioinformaticians, don't send many candidates to the FDA, only send them if you know that they're likely to be good, if you're really convinced. That's where the private knowledge comes in. So the FDA, on the other hand, doesn't know any of this, but they give these candidates, and it just happens they're all good candidates. And then they screen them at the 0.05 level, and all good candidates go to market, and everybody's happy. All right, the problem is it's more like the thing on the right is what really happens. There's a large profit to be made. It's $20 million to run the trial, and if you're approved, you might make $2 billion in a year, ibuprofen or something. And now the CEO can do the same calculation. She says, if counterfactually my drug is not effective, I will make an expected profit of $80 million. How could that be if the drug is not effective? Well, I'm going to throw all my candidates up at the FDA, good or bad, and because of the 0.05 false positive rate, a good number of them will go through, and the profit is so high, if I even get a few of them through, I'll make money. And this is what happens. And now a couple of years go by, and that drug has been on the market, and people have been taking it, and there's been no effect. So you didn't hurt anybody, but you did hurt people because they could have gotten a better drug maybe, and they could have lived, but they didn't. So this is a problem. All right, so I believe the right way to think about this is contract theory. The problem, though, is it now has to be statistical contract theory because we still have to do the clinical trial. And we have to see what are the incentives in the clinical trial. Okay, so much briefly now, here's the problem we set up, and we turn it into a math problem. We defined a statistical contract to be something of the following form. It's an opt-in protocol. If you're the pharmaceutical company, you look at this, you say, I don't like this setup, you can walk away, fine. If you opt in, you pay the reservation price R, 20 million. You now choose a payout function from a menu that we designed. And the payout function is going to be a mapping from the statistical trial to some kind of licensing terms. Okay? And we will give you just like with business class and economy class, we'll give you a list of mappings that you get to choose, depending a little bit on your internal knowledge. All right, so that's what we do. And now you run the clinical trial. Z is data obtained from a distribution P of theta. Now, theta is the true theta that nature knows, because nature knows the truth. We don't know it, but nature knows it. So they give you true data. And now the agent gets a payoff F, which is their licensing terms they picked, but it's a function of the random observation Z. And the principal you see is the utility that depends on F also, because they have to pay that out, and depends on the true theta, because over time it'll be clear whether the FDA is doing their job or not. So that's the setup, and now you can analyze this mathematically. You can say, what are the Stackelberg equilibria? What's the revenue? What's the false positive rate? What's the false negative rate? Can you control statistical error while maximizing revenue? And so you can do all the math, and we've done that. But most interestingly, we can actually tell you what the form of an optimal contract is. And that's the thing I want to highlight here. So first of all, when you do this kind of analysis, the first thing you have to do is say, what does it mean to be incentive aligned? Because you have these strategic agents, you can't just write down a dynamical system. You have to say, are they going to participate or not? All right, and so in this case, it's pretty straightforward. The expectation under the null hypothesis, that's what P of theta naught is. That's the null. The null means the drug is no good. All right, so under the null, the expectation of the amount I'm going to have to pay subtracted from the amount I'll gain, that should be negative. Otherwise, the FDA is just giving people money. Okay? So it's pretty straightforward. It's an expectation under the null. Under the null, that's very common in statistics. P-values. It's a tail probability under the null. Okay, it's how we do a lot of inference. Okay, so we can say, okay, that's what it means to be incentive aligned. Now, can you tell me what the payoff function should look like if they are incentive aligned? What are the family of functions that are incentive aligned under this definition? Some set of functions. It turns out there's an if and only if statement, that a contract is incentive aligned if and only if all the payoff functions are what are called E-values. All right, now E-values are kind of a new tool that we are using in statistics these days to replace P-values. As I alluded to, P-values are a tail probability under the null. What's the probability under the null that you're out in some tail? And then you would reject the null. There's problems with p-values. You can't put multiple p-values together. You can't do stopping at any time. They have classical problems. E-values are different, but related. They are a random variable that's non-negative, and its expectation on the null is less than or equal to 1. So it's a random variable. It's not a set. And the expectation being under the null being less than or equal to 1 is kind of like a wealth amplification idea. That if under the null you're not amplifying your wealth, that's a sign the null is true. If on the other hand you're amplifying your wealth, it's bigger than 1, then that's a sign you should reject the null. So it becomes it's a game theoretic interpretation of probability theory. And anyway, there's a characterization of e-values. It's not just non-negative random variables, it's non-negative super martingales. That's the big family in general. All right, so that was known already in statistics, that e-values, you can now do optimal stopping, so you can stop at any time, you can put them together. It has a lot of nice properties of statistics. But what we did here is to show that the e-values around 1-to-1 corresponds with optimal contracts in statistical contract theory. All right, so that's a connection at the foundations of mechanism design and statistics. So we've gone back to the FDA, we're talking to them, and we have a lot of other projects underway on pushing this. I'm not going to spend more time on that. I'm going to turn to my other two little vignettes. All right, so this one is a second project where we have information asymmetry. It's a little less about incentives, but I think it's an important enough information asymmetry that I want to discuss it here a bit. Here's all my students at Berkeley who worked on this with me. We call this prediction-powered inference. So prediction refers to these big neural network, ChatGPT or AlphaFold kind of systems. And inference refers to putting actual error rate control on these things, which have been so far not having such control. Okay, so as I'm sure you all know, things like AlphaFold now exist, and they are extremely accurate at making predictions. Accurate overall over the training test data splits. And so this allows us to start thinking of doing science with things like AlphaFold instead of with doing lab work. Because in particular, there's hundreds of thousands of amino acid sequences where we know the crystal structure, so we know the actual three-dimensional structure. But you can generate hundreds of millions of sequences predicted by AlphaFold. And AlphaFold is very accurate on the known sequences, so why not use AlphaFold instead of using the actual lab work? Lab work is expensive and slow. And hundreds of thousands might seem like a lot, but there are huge, vast numbers of proteins out there, like in viruses and phage and bacteria that we don't know anything about. So, massive undercounting. So people have been doing this. They said, let's look at some statistical hypotheses and test them using AlphaFold. So here's an example. Back in 2004, there was an important study done you're looking at quantum disorder in proteins. Okay, so as you I'm sure know that proteins mostly like to fold, but occasionally there's some quantum fluctuations that make there's kind of strings falling down. That used to be thought that was just a broken protein. That wouldn't be in nature. But it turns out that if you take those strings and you put multiple of them together and you can make grids. And now you can put these grids in the membrane and you can let things in and out of cells. And so quantum disorder turns out to be a control mechanism in cells. That's now increasingly well understood. But back in 2004, they had no idea. They just thought this was an interesting thing to test. So how do you test this? Well, you look over your entire protein data bank and you say, quantum disorder, yes or no? Phosphorylation, yes or no? That means it's an active protein. It's a little 2x2 table. You do a statistical hypothesis test with an odds ratio. You get the odds ratio at some number, and then you get a confidence interval in that. Does the confidence interval cover 1? Okay, classical. They did that, and the confidence interval sadly was huge, and it covered 1, so they couldn't make any conclusion. Someone came along in 2022, and they said, let's redo that whole experiment with AlphaFold. Now we can get 200 million data points. They're not really data points, but they're predictions that are extremely accurate. So let's just throw them into this little 2x2 table and redo everything with AlphaFold as the data. All right. Now this is happening all over the place. Here's just some papers we found from 1 week in Nature and Science doing this kind of thing for things like electricity access, regulatory DNA, econometrics problems, and so on. So it's happening all the time. This is what's called AI for science or whatever buzzword is being used. All right, now is this a good idea? Well, maybe, but it's got some very serious problems. And so this slide I'm going to take a moment to explain. So we redid the whole big AlphaFold experiment. We took half of the data and we held that and we did a Monte Carlo to get a ground truth idea. And then we just held that and never looked at it again. On the other half of the data, we redid their experiment. So we got the ground truth being that dashed line there. The x-axis here is that odds ratio. So a number bigger than 1 says there's an effect, a number at 1, there's no effect, and you need to get a confidence interval. The confidence interval coming from the AlphaFold data is that gold region there. As you can see, it's extremely narrow. It's very sure of itself. Okay? Why? Well, it has 200 million data points. So it's very sure of itself, but it's not even close to covering the truth. So it's sure of itself and it's wrong. Okay? So a statistician would look at this and say, that was a bad idea. Let's use actual data. So how much data is now in the protein data bank? Well, 100,000 data points, not just 10. So if you rerun the old experiment with 100,000, you get the gray region up there. It's still a huge confidence interval. It still covers 1. You still can't make a conclusion. Wait 10 more years. All right, so this is a conundrum. Long story short, there's a way to fix this. So this PPI idea uses both data sets, uses AlphaFold, but not only AlphaFold. It corrects the bias in the confidence interval. Okay, so it's very common in statistics to correct the bias control. What we're doing is collecting the bias in the confidence interval. That's a bit new. All right, that's the green region there. That's our PPI interval. And you can see it's much narrower, more narrow, but it's still got uncertainty, but it doesn't cover 1 anymore, and it does cover the truth. So it provably covers the truth, and it is provably smaller than the classical statistics one under certain assumptions. And I want to say what those assumptions are in a moment. So first of all, why is this happening? Well, after we saw this, we went back to the original data and we said, wow, AlphaFold's not doing so well on some of our proteins. In fact, here's a prediction from AlphaFold on the left, and there's the actual structure. So you can see there's quantum disorder in this protein. And AlphaFold was making lots of such errors. Why? Well, there's not lots of data in the AlphaFold training data with quantum disorder, because people weren't interested in that when they collected all the original data. Scientists are always interested in new phenomena. You're always going to be on the edge of knowledge. You're almost always going to have this phenomenon happening because you're looking at new things, not the old data. So yes, AlphaFold is accurate overall on the past. That doesn't mean it's a good guide to the future. All right, so this is a key issue that is really being missed by a lot of people in science right now. All right, so just to show you, here's another example. If you look at the thing on the lower right there, you see again, machine learning confidence interval is not covering the truth. The new one is covering the truth. And then here's a nice one for honesty. Here's one. It's some econometrics problem of predicting income. And you can see the machine learning model is really terrible. It's very sure of itself and very, very far from the truth. Hugely biased. All right. So our new confidence interval, the green one there, is covering the truth, but it's not so much better than the statistical one. That makes sense because you're using the machine learning model, which is a terrible machine learning model. That doesn't mean you give out an arbitrarily bad answer. You still cover the truth. It's just that you don't get much gain. Okay. How do we do this? I'm going to show you 2 pictures, and I'm not going to explain it. It's in the paper. It's not hard to understand, but it's just sit down over lunch or whatever and go through it. You will understand it. So just really briefly, we identify what we call a rectifier, which is in the population of all possible proteins. What's the true parameter, the true odds ratio, and what's the true one that AlphaFold would have if it had all the world's data? So that the difference is a kind of a generalized bias. That's a population parameter. You can get data to make a confidence interval on that rectifier. Okay, so then what we do is we actually get the real data and we calculate the AlphaFold estimate, which is some biased confidence interval, and then we look at all the possible rectifications, which are high probability under our sampling regime. So we correct the confidence interval, and that's what delivers this new confidence interval. Here is a little bit of math, just to give you a little flavor. This is for M estimators, meaning that they're defined, theta star is the argmin of an expectation of a loss. So many estimators are of this form. And so now you look at the gradient of that loss, call that G. And now by definition, the expected value of G is equal to 0. That defines an M estimator. And so then we take that expectation, set it equal to 0, and then add and subtract a term, and we get that green thing and the yellow thing. And so the yellow thing is something we can just estimate as a point estimate, and the green thing is what we call the rectifier. It's a difference of expectations of gradients. We can estimate that with a confidence interval, which I call R theta, and then we take a point minus a set, and we get a corrected set. So that's kind of the mathematics here in the case of M estimators. And you put all it together at the bottom, you can prove a theorem that says we cover the truth with an asserted probability. All right, how much time do I have left? 10 minutes, perfect. Okay, so I'm going to now return back to the more economic side of this. We're going to talk a little bit more about incentives, a little more about regulation. There'll be probably even less math. There'll be a theorem here, but really this is more about how do you set up the problem? What are the ingredients needed to think about this? And now that I am in Europe, I do want to spend some time in some governments and talking about these things because there's not enough. I mean, the machine learning people that are going in there talking about it don't talk about incentives and regulation at all, and it's really becoming a headache. These are my colleagues, Nivasini, Elireza, Nika, and Mina at Berkeley. All right, so let's talk about privacy, first of all. This is one of these words you hear a lot if you talk about regulation. The government people, the newspapers are full of talk about privacy. Privacy is both good and bad. Okay, what do I mean by that? All right. Well, we talked earlier about price discrimination. You give people different prices depending on their willingness to pay, because I really want to go to Helsinki tomorrow. I'm willing to pay a little bit more. If I deliver that information, that might be more likely to get a seat. Similarly, insurance rates may depend on price. If I'm a little older right now, I'm over 65, and so I can get a cheaper fare and to get into the theater, which is fantastic. And I really want to deliver that information that I'm older so I can get my cheaper fare. All right, so if I had perfect privacy, you could know nothing about me. I could not get any benefits from my older age. So people often want to give up a little privacy in return for getting some economic value. But even with things like their medical data, my genome, that's very private to me. I'm not going to just write it up on the board here. But if you ask me for my genome and you're a medical doctor working on a disease running my family, I'm going to say, yeah. If you're an insurance person, I might give you a little data just to help social insurance rates. But it depends on who you are and what the situation is, the context. So I want control of a privacy knob. I don't want to just have some lawyer saying, here's the setting. Okay? So therefore, it must be there's an economic story here. If I have control over it, I'm going to turn the knob depending on my gain or my benefit, my loss. All right? Okay, so now if we think about this in the domain, say, of monopoly pricing, so a monopolist has a product they want to sell, and they're going to set a price, and the price they will set will be a little bit higher than the market price. That's the monopolist's price. But if they set it too high, no one will buy it, so there's a trade-off. And so now you could ask in this situation, if you know a little bit of my willingness to pay, what price will you give me? And so now we're talking about market segmentation, which is very commonly done in economics. And so there is a very famous paper by Dirk Bergman and colleagues in 2015. So under situation, I'm not going to get into details here. You have consumer utility on the X and producer utility on the Y. All right. And there is a triangle under all possible segmentations of the consumers. What utilities can you get? Okay. If I segment it a certain way, certain consumers will be happy, others will be less happy. The aggregate consumer utility, then some of them will buy less or more, therefore that'll lead to more producer utility. And if you look at all possible segmentations, they did a theorem which said it's a triangle, all right? And now regulators look at this triangle. It's a famous triangle, and they design market control regulation mechanisms based on this triangle. And I could go through each of the interpretations of the Q, T, and R. So pretty important to be able to write these kind of things down. Okay, so on this slide, I showed you what we've done here. We've said we take the true market, we're going to be segmenting it, but we're also going to put a differential privacy mechanism in here. So instead of the producer getting to see the true market, they get to see one where noise has been added to the data. Okay, so this is particularly something called randomized response. If I ask you for an answer, you're going to toss a coin, either give me the truth with probability P, and give me a complete lie with probability 1 minus P. It's called randomized response. So we're putting that mechanism in between here, and we're going to ask, how does that change the utilities? So it's a very natural math question. And so we were able to solve that math problem. And it turns out that triangle of Bergman et al. Now becomes a high-dimensional polytope, which gets projected down to 2 dimensions. Okay? And we can characterize that polytope. It gives you something a little not quite triangular. And it does a couple of neat things. First of all, it shifts the whole blue region a little bit to the right. That means you get the lower bound on consumer utility is no longer 0. You can get positive consumer utility, which is really nice. You want to have that. Then producer utility comes down, at least in the worst case, but it also can come down not in the worst case as well. And so you can now reason about where you want to be in that thing depending on different segmentations. All right, so we show in summary that you can hurt the producer utility by reducing its maximum utility, but you also reduce the minimum and you help the consumer utility. So these are some of the qualitative things that come out of this analysis. So Let me show you another example, which has even more clarity about the regulation issue. So this is going to be 3-layer Stackelberg games. So Stackelberg is usually just a principal and an agent or leader follower. But what if we have 3 of them? What if I'm both a leader and a follower? Because I'm in the middle of a hierarchy. This happens actually in real life. So this is not a great picture here. But here we have users, you and me. We're sending our data up to some service like MasterCard. They're providing a service back to us, payment or whatever. And MasterCard does not make enough money on that service alone to be in business. They make money also by selling data to data buyers, which use that for all kinds of purposes. All right, is this a good system or not? Well, it kind of depends on what all the utilities are, you know. All right, so now you start thinking about the incentives, it gets pretty interesting. If I send data up to these platforms, I know they're going to be selling some data to data buyers. I want to have a little privacy. All right, so you have to make a guarantee you add a certain amount of noise. How much noise do you add? Well, that's a business decision. You could advertise. I'm a very private company. We will add a lot of privacy. Other companies says, no, not so much. I will know that. All right, now if it's one that guarantees a lot of privacy, I may send more data to them, or they may get more data. Therefore, their model can be better. All right. The data buyers, on the other hand, are looking at this data saying, from the company that has a big privacy guarantee, and they're saying, well, if we get data from them, it's got a lot of noise added to it. That's worse data. So they're less incentivized to go to that company and give them money. So the guy in the middle's got a kind of incentives going both ways. All right. And so now if the data buyer says, well, I'm not going to go to that company because there's noisy data, but then they realize because there's a privacy guarantee, they're getting more data from the users. And so they'll get more data, and so they also have a complicated problem to think about. Long story short, it's a math problem. It's a Stackelberg game with 3 layers to it, and you can write it down, and you can find equilibria of this game, and we've done that. Here's kind of our model, briefly, some pictures of the utilities. And at the end of the day, we were able to make recommendations for privacy regulations. So as you all know, in Europe, GDPR is around, that you're having to click all the time now on, yes, I know you're using cookies. Yes, I know you're using cookies. But it's actually hurting lots of small-scale producers. Okay, lots of small companies are dying because of the GDPR. And the big ones aren't getting hurt. So it's not really, these are issues that need to be worried about. So what does our model actually suggest here? Well, we have this, is this the slide I wanted? Yeah, I guess so. Sorry. We're able to show you that if you have maybe, say, 2 kinds of platforms, low cost, which have to sell data to stay in business, and high cost ones, which don't need to sell data, like Google. And now you can sort of show that if you have a minimum privacy mandate, that all of them have to give a minimum level of privacy, that's actually good for user utilities. But we can also further increase user utility by having a non-uniform privacy mandate, which puts a higher mandate on the low-cost platforms. All right, and so the kind of intuition is given here. But this is the kind of thing I can sit down with a government regulator person and explain this to them. They don't need to know what a Stackelberg equilibrium is, but they can understand that slide. And I think this will make them make better decisions. All right, and then the last one I think I'm going to kind of skip a little bit, but just people are also talking not just about safety, but about privacy, but about fairness and about safety. Again, those don't sound like economic quantities, but they are. If you want to be fair, there's a trade-off. How fair? How much? Who's going to lose? Who's going to win? How much do I care about it? Safety, very similar. It's got to be put in an economic context. So we've done now contract design with safety concerns, where people need to be incentivized to do safety checks. It costs them money to do a safety check, but I may audit them, and if I audit them and they didn't do the safety check, they will lose. That's bad utility. But they might not get audited, and therefore they get through. That's good. And so you work out all of the equilibria there as well. So that's the kind of problem we've been working on there. Okay, so I'm finished. Let me go back to my original sort of points a little bit. So one point I made earlier on the talk, which is that intelligence, whatever you mean by it, is not just about a human intelligence. And this AI idea, I really hope you'll agree, is not helpful for our current dialogue about engineering systems. And so what could be better? Well, thinking about the collective and thinking about systems. And that's why I'm glad to be in a control theory audience. You already think about systems. I just want to maybe expand your horizons a bit, think more about economic systems as well, and more about data flows in your systems. Putting all that together in a control perspective, I think, is really going to be important going forward. In particular, if we think about this as kind of an emerging engineering field. And in fact, here's my last little slide. Here's what I really think is happening in our era, is that every 50 years or so, a new engineering field emerges. And I mean the big level engineering field. So chemical engineering arose in the 40s and 50s mostly. There was a little bit before that. But in the 40s, 50s, it arose. Before that, there really wasn't chemical engineering. What did you have before that? Well, you had quantum mechanics. You had fluid dynamics. You had thermodynamics. So you knew what happened in a test tube when you put chemicals together, how they would mix. But the idea that you could build a factory and have them mix at vast scale and produce polymers or chlorine, no one knew that was possible. It was a dream. People tried it, and it sort of worked. It sort of sometimes exploded. And sometimes the factory just didn't work, and so on. But it took about 20 years. It got to be possible, and then a field emerged called chemical engineering. Now, chemical engineering is a serious engineering field. It's got its own mathematics. There's new thermodynamics and new principles in it. It's not just chemistry. Same thing with electrical engineering. You go back 50 years before that. Before electrical engineering, around 1900, you had Maxwell's equations already. So you had they understood the phenomena completely, right? But the idea of how could you bring electricity into a home and not burn it down, or take the waves that Maxwell's equations gave you and put communication on that, or build circuits, that was all not clear. And that developed over time, both with practice and with the new mathematics, and it got called electrical engineering. Now, in that era, I don't think people realized, oh, we're doing electrical engineering. They just kind of did it. I think the same thing is happening right now, and I think that we don't have a good name for this field. Cybernetics might have been a good name. But what is it? Well, it's kind of Internet of Things. It's lots of devices everywhere. But it's also data flows. These devices are measuring things, they're sending things. And there's economic value associated with the flows because there's actors and humans involved in all this stuff. So like a healthcare system is an example of an overall system that has got human utilities, it's got value, it's got flows, and it's got utility functions. You die or you don't. Transportation systems and so on. And all these systems have enough similarities now where it's kind of clear we're building something that's, there's a platform, it uses cloud, GPU, it uses this and this and this. And it uses all of our engineering ideas from the last century, but it's somehow new because it's got all the humans in there and all the human data, and it's got all the microeconomics as well. All right, so I don't have a name for this field, but I just think this is what's happening. When people say AI in the newspaper, that's what they mean, that a new engineering field is arising. And we don't know how to talk about it. We don't know how to think about it. We don't know how to regulate it. We don't know how to do it. Calling it AI is a bad mistake because it leads to the Elon Musks and Altman saying stupid things. But calling it cybernetics might not be better. So you could call it control theory. So I leave that as your option to go make that into something. Thank you.
Thank you for a very inspiring and challenging presentation. I think we have time for 1 or 2 questions. If you want to ask a question, please raise your hand because we have people with microphones. Okay, so then I'll do it myself.
Okay.
So you had this triangle with the statistics on top and economics and computer science, and you asked, where is control? So I'm imagining this table where people, where they're putting people of different competences, and in the corner of the computer science they put Michael Jordan, and they say they have the best scientist in the world in this corner. But what they don't realize is that they don't get a computer scientist actually, because they get a guy who is trained in control from the beginning. Is that correct? Yeah?
Yeah, it's correct. I guess this is kind of for the young people in the audience, is that I would encourage you not to be at one corner. The whole point is to be in the middle of the simplex.
Yeah, so maybe the lesson for us is not so much the labeling, but that we should educate people who can take any of those 3 hats, and depending on the context.
Right. That's right. And if you learn the mathematics of control theory, which I did, optimal control theory, Pontryagin, a little bit of differential games, a little too much Gaussianity. I had to leave that behind at some point. But you learn the mathematics, then you're kind of in flows and you're prepared to actually get the best ideas out of each of these fields. In fact, the computation side, computer science, it's not really computer science, it's optimization theory. That's what's driven all of these developments, optimization theory. So optimization theory, it's not really part of computer science, that's something a little different, but it's algorithmic. It's how do you build algorithms that do things. And if you're a control theorist, you already have a pretty good idea about optimization, and you could get a better idea. You could think about how to do that in a million dimensions with non-convexities. That's not part of your training, but you can learn it very quickly given your background. So I think of control theorists as really kind of like the physicist of the finance world. They kind of come in and they can look at the problem, they can think in new ways, and they can integrate across the whole simplex. But I really want to encourage you to get out of like H infinity and linear systems and get out of the classical control problems. Open up. Open up, folks.
Okay, thank you very much.